everyone. So the last thing that I want to talk about is I want to continue with the vertical projectiles. This time I want to talk about throwing the objects upwards. Now, realistically, nothing really changes. The only main difference is that the velocity now becomes is initially positive. There's a few other things that we have to note. For example, when it's thrown up, they might say the phrase maximum height. Typically, one thing that you need to know is that at maximum height, the velocity at that point is zero. There are some other tricks, like for the fact that when it's symmetric, there's some things that you can figure out about that. I'll go through that when we get closer. The one thing I do want to point out is the previous projectile problems that you've done, you may not have had to worry about making the acceleration negative or the velocity negative. You might have found that you pretty much get the same answer regardless. In this specific case, it actually is extremely important that we make sure the acceleration is negative. Now, if you've been making sure to put the negative in every single time, as well as the velocity, then there shouldn't be an issue. Typically, what I recommend is when you're going through the vectors, the position, the velocity, the acceleration, instead of just writing down what the number is, always ask yourself, is this a positive or a negative? It's positive if it's going up, negative if it's going down. All right, so here's the first question. So pause video works off. We'll go in a second. All right, so for part A, it wants to know the maximum height reached by the ball. So like I said, we know that the velocity at that point is going to be zero. So I'm going to state that wherever it started is going to be zero. I'm looking for that final height in the problem. The initial velocity is a positive 15 because it's being thrown upwards. Again, at maximum height, the velocity ends up being zero. The acceleration is negative 10 because it's being pulled downwards. And I also don't know the time. Now, one thing to remember is that with a lot of this stuff, that besides like the final values, final position, final velocity, and time, it's not something that is always the very last thing. Typically, those final values are relative. It's wherever you want to end the problem. If you want to end the problem right when it reaches its maximum height, that's what those final values are representing. If instead you want to use those values to represent when it lands, that's what they're going to end up representing. As long as you're consistent, there's not going to be an issue. So you just want to make sure that the velocity that you choose, the final velocity, and the time and the position you choose all make sense. For example, if you use the time that it's in the air for the entire trip and you use the velocity right when it's at max height, that's a conflict of information. So as long as you're consistent, there shouldn't be any issues. Now, based off of this, if I want to find the maximum height, the only equation that really works out is the timeless equation. So I plug my numbers in and I get my answer of 11.25 meters. So that's the maximum height reached by the ball. Now, part B asks, how long is the ball in the air? This is kind of worded a little bit poorly. It's referring mainly in total. So if we go back to the original problem, it says that it was caught at the same height. I didn't take that into account here because I essentially ended the problem early. But now that they want to know how long the ball was in the air, I'm going to end it at its final position, which is the same height it was thrown at. So one thing I'm going to say is that the final position is zero because it starts and ends at the same spot. My initial value stayed the same, so initial velocity is still positive 15, acceleration is still negative 10, and I'm looking for the time. If I use this information, it's very clear that I can use the annoying x equation. So I plug my numbers in. Normally, if I had a term for the x values, I'd have a quadratic, but here I can actually divide out a t from each section. And when I solve this, I get t equals 3 seconds. Now, one of the nice things about this is that this is not the only way to solve the problem. Another way that we could have done this is we could have went back to this setup and figured out the time it took for it to reach its maximum height. If we did that, if you do the math really quickly, it actually turns out to be 1.5 seconds. So because the ball is being thrown and caught at the same height and it's being affected by the same acceleration throughout the process, this is what we call a symmetric pathway, a symmetric projectile, in the sense that everything about the object going up is the same as it going down, just in different directions. For example, the time it takes for it to go up to its maximum height is equal to the time it takes for it to come down from the maximum height, as long as it's being caught from the same position. So you could have done that, found the time to max height, doubled it, and you would have gotten to 3 seconds. There's a second thing you could do. Because this is a symmetric problem, we can actually use this equation because we do know what the final velocity is in a symmetric setup. Just as I said before, just like how the time is the same going up and coming down, it turns out that the velocities are also the same. If it gets thrown up at 15, it's going to come down at 15. But I have to make sure that I note this as negative 15 as the final velocity to show that it's going downwards. And once again, when I use this equation, I get 3 seconds. Just note that you can only do this if and only if you have a symmetric projectile. All right, so here's the next question. Pause the video, work itself, and we'll go over it in a second. All right, so part A wants to know what the initial velocity needed to achieve this. Again, there's a bunch of different ways that you could have went about this, so I'm only going to show one way. Again, I'm going to say that, where he starts, that's 0. Also, the fact that he's landing at that same height is also 0. I don't know what the initial velocity is or the final. The acceleration is negative 10, and the total time is 4. So from this, I can actually use the annoying x equation, plug my numbers in, and I get 20 meters per second. Now, I don't think I do this. I don't think I show this example. Yeah, I don't show this example, but one thing I could do is I could have said that this is x and this is negative x. Again, taking advantage of the symmetry, and then use the same final equals initial plus acceleration times time would have been negative x equals x plus negative 10t, or negative 10 times 4. Move the x over, so I get negative 2x equals negative 40. And we could see that when we divide by negative 2x, we get the same initial velocity of 20 meters per second. So this is, like I said, if you have a symmetric problem, you can make your life easy by remembering that the velocities are going to be equal but opposite. All right, so for part B, it wants to know the maximum height reached by the basketball player. So again, I'm just going to write down all my information. Pretty much this typical stuff. I do have the time there. I could use it, but I'm not going to use it right now, or at least I don't think I'm going to use it. But everything pretty much stays the same, except the initial position is now 20. Initial velocity is now 20 meters per second, and the final velocity, because I'm now going to stop it right when it reaches its maximum height, is going to be 0. So I'm going to use the timeless equation, plug my numbers in, and I get 20 meters. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So what I'm going to do is, like always, write down everything that's given. So I'm initially starting at 10 meters in the air. I'm going to end up landing on the ground. Because it was dropped, the initial velocity is 0. I don't know what the final velocity is. I don't know what the acceleration is, but I do know the total time is 4 seconds. So based off of this, very clearly I can do the annoying x, plug my numbers in, and end up getting that the acceleration is, I didn't put it here, but it's negative 1.25 meters per second squared because it's going downwards. One thing to note, it actually is pretty useful to almost remember these like what equations you can use based off of what information you don't have. So, for example, if we're not given time and we're not using time, use a timeless. That's kind of what the name implies. But for this equation, I knew that I was able to use this because the only variable that I didn't know the value of was the final velocity, and that was the only one I didn't care about. So, that kind of leads me to know which equation I should be looking at. So just try to keep that in mind as far as, you know, trying to help you through figuring out what equation works best. All right, so here's the next question. Pause the video, work itself. I'll go over in a second. Now, as I mentioned before, a lot of the questions in the EP are not going to be your typical plug and chug calculation type questions. It is extremely important that you know how the equations work so that you can answer some of the conceptual questions, but it's also good to have practice doing conceptual questions. So that's what this is. This is actually something that would pop up on the free response where they give you claims and you have to identify what part of the claim is wrong and what part of the claims are right. Just like how a lot of times when you are describing something to someone or maybe writing something in a lab, you might accidentally make both a correct claim and an incorrect claim. It's important that you kind of recognize that. So I'm not going to play the video, but there's a clip from Star Trek, I think Star Trek Into Darkness, where they're falling and they pull on the parachute. It happens very quickly, but it's a really good example of the typical moving reference frame type questions with the whole relative velocity. I highly recommend looking at that because throughout the entire process, the camera is constantly following one of the characters, and you see all the other characters when they're pulling their chute and how it will look from his perspective. So this first claim, the correct statement that he says is he says that when the parachute is pulled, it causes the person to have a net acceleration upwards. This is actually caused by the fact that when the person's falling, we have an acceleration pulling him downwards at -10, and air friction, which if he's moving at his terminal velocity, will be pulling up at the exact same acceleration of -10. But when he pulls the parachute, all of a sudden he increases the effects of air friction. So now this upwards acceleration caused by air friction skyrockets, becomes much bigger, probably gets all the way up to -30 or something. And then we end up having a net acceleration upwards. Now we also know this because the whole point of a parachute is to slow someone down. And as we mentioned before, the main thing about acceleration and velocity is that if you're slowing down, those two things are in opposite directions. You're falling down, therefore, if you're slowing as you fall down, that means that your acceleration has to be upwards. So this is the correct statement that he makes. The incorrect statement, he kind of says two things. The first incorrect statement is which remains until he lands. Not necessarily true because again, as he slows down, this upward acceleration caused by the air friction will start to decrease. Because remember, air friction or the effect of air friction is related to how fast you're going. The faster you're going, the bigger the air friction, which is why the parachute ends up having this big effect because you're technically moving faster than the terminal velocity of the parachute. So eventually you'll slow down enough so that you move at your new terminal velocity, which will result in a zero acceleration. So that first statement's incorrect, and then the other statement is he moves upwards. I'll discuss this later, but again, the whole point is he's still moving down. He's just slowing down. The only reason that it looks like he moves upwards is because of the moving reference frame. But yeah, this is another incorrect statement, is that he doesn't actually move upwards. It only looks like he moves upwards. So student B kind of says something similar. Now, one of the nice things about these, identify the correct and incorrect statements is if you have multiple statements, it'll be pretty clear what type of statements you're looking for. So because the statements that we found that were either correct or incorrect were things like the direction of the net acceleration and him moving upwards or not, those two statements are going to play a part here. So clearly, this student is going to have statements that conflict with that. So if we look at the correct statement, kind of counterbalances the other student. He mentions the same idea that I said before, that the person doesn't actually move upwards, it only looks like he moves upwards. And that's because of the fact that the camera, which is one of the character, Captain Kirk's point of view, is moving faster than the parachute is. Therefore, it's going to look like it's moving upwards because he's going to be pulling further and further away from it as he falls faster and faster. As far as the incorrect statement, the fact that the person says that the net acceleration is never upwards. Again, there is an acceleration. Typically, this is actually a really good question because a lot of people tend to confuse acceleration and velocity. A lot of people think that if you are moving in a certain direction, then your acceleration has to be in that direction. Or if you're accelerating in a direction, your velocity has to be in that direction as well. That's not the case. They can always be in different directions. In fact, many times they are going to be in different directions. So yeah, that's how you end up doing that. All right, here's the last question. Pause the video, work itself. We'll go over in a second. All right, so here we end up having the situation. I want to make sure that I don't accidentally draw on it. So the person's kicked up, comes down, and then falls here, and we want to know this distance. So what we're going to say is that we're going to assume that this is 0. We don't have to do that. We actually could have set this equal to 0 and say that the final position is 0 and basically look for the initial position. Again, apples to apples, same thing, potato, potato. So I'm going to say that the initial position is 0 and the final position is what we're going to look for. Because it is below my 0 point, I know that this is going to be some negative number. So I know I'm on the right track when I get a negative position. Because he's being kicked upwards, we have a positive 25. I don't know what the final velocity is. The acceleration is going to be negative 10, and the time is going to be 15 seconds. Nice thing, I just plug it in to the annoying x's equation, plug the numbers in, and we get our answer of negative 750 meters. All right, that's pretty much it. Like I said, there really isn't that much that you have to worry about with vertical projectiles. Realistically, again, doesn't matter if it's being dropped, thrown down, or thrown up. The thing that you have to just be careful about is what you plug in here as far as sign wise, and making sure that you have your sign here correctly. If you can make sure that you do that and you get into this habit of writing down everything and putting zeros kind of where they logically make sense, making a diagram and kind of creating almost like a graph overlay over this, saying that this is going to be your positive direction, this is the negative direction. Later on, when we talk about horizontal projectiles, we'll kind of have this also be, the positive x direction, starting 0 here, doing all that good stuff. As long as you kind of get into the habit of doing it now, there really isn't going to be any such thing as a tough projectile problem. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.